Okay, welcome to lecture number 47. In lecture 47, we have a good number of theorems to do. But before that, let us define two circles are called touching circles. If they have only one point in common. There are two situations. Two circles are called touching circles or tangent to each other when they have only one point in common. This is external tangent, internal tangent, externally touching, internally touching. Now the theorem is, if the circles are touching circles, then the centers M1, M2 and say point of contact T, they are collinear. This is our first theorem. In both the cases it will be true. M1, M2 and T. So the normally given proof in this case, which is not correct, is to draw common tangent here and say that this common tangent is perpendicular, this common tangent radius segment is also perpendicular, and therefore there exists a unique tangent between two circles, therefore they are collinear. That is not correct proof, because you are assuming that the 3 points are collinear in this proof indirectly, and therefore we will not be able to consider this proof as a correct proof, because if you draw tangent to this circle and if you draw tangent to this circle, they could be two different triangles, and unless these 3 points are collinear, those two tangents will not coincide. And so if we are assuming that there exists only one tangent between the two circles, that means we are assuming that there are 3 collinear points. So the proof of this will go like this. Suppose, if possible, M1, M2 and T, radius R1, radius R2, if possible they are not collinear, they form triangle. So we create a triangle. Now we can always reflect this point T and get T dash. Okay, and after reflecting this point T over here, this is congruent to this is 90 degree. Hence we can show that M1T, M2 T dash, M1T, M2 T dash is a kite. We can prove that these two triangles are congruent by SSS, and therefore there is not only one point which is common T between these two circles, circle with center M1 and circle with center M2, but there is one more point T dash also which is common to these two circles. That means the given circles are not tangent circles. So if the two circles are tangent circles, then they have only one point in common, and the point common is collinear with the centers, is proved, because if we take it otherwise, there exists a triangle and they get one more point of contact, and hence the circles which are given to be touching circles are not touching circles, they have more than one point in common, they are intersecting circles. So contradiction. So this case also it will happen, in this case also it will happen. The diagram in this case will be something like this: M1, M2, T and T dash. Proofs will be exactly same, right? And hence we assume, we accept that the centers of touching circles are collinear. Then the next theorem that we have is 3 circle theorem. If we have 3 circles which are intersecting each other, then their common chords are concurrent. If we have 3 circles which are intersecting each other, need not be congruent, then their common chords are concurrent. Say AB is a common chord of circle number 1 and circle number 2. This is circle number 3. CD is a common chord of S2 and S3. Then if we join E and F, they will pass through the point of intersection of these two. That is what this 3 circle theorem is all about. Now we will prove it. Pause the video, spend at least half an hour to check whether you can do it independently or not. Else look at the solution. Maybe I will have to draw the diagram again, because I don't have space there to work with. So the solution goes like this. we have a circle, we have a circle, and we have another circle. This is AB, this is CD. So we draw two intersecting chords, we get point of intersection, say P. We join EP and extend. If possible, it does not pass through F, and it intersects at Q and R, S1, S2, S3. Okay, so we know the theorem PAPB is equal to PCPD for two intersecting chords. Therefore, if we apply PAPB into PCPD for circle S2, we get PAPB is equal to PCPD. If we apply it for circle S2 and S3, S2 is done, S3, then we get PCPD is equal to PEPR. And if we apply it to S1, we get PAPB is equal to PEPQ. Now, if you observe these three equations, we realize that these two quantities are equal and these two quantities are the same. Therefore, these two quantities are equal. Hence, these two quantities are same. Out of which PE is PE, therefore PR is equal to PQ. So, this implies PR is equal to PQ. So, R point which is on circle 3 and Q point which is on circle 1, they are supposed to be at same distance from P, and that is only possible if it is equal to PF. So RQ and F cannot be three distinct points, they have to be same, and therefore this line EP that we have drawn must pass through F. This proves concurrency of common chords of three intersecting circles. Now, the application of this theorem is in proving concurrency of altitudes. We have triangle ABC, and if we draw altitude AD, with AB as a diameter, if we draw a circle, then that circle will pass through D. Why? Because ADB is 90 degree. If we draw a semicircle, circle means this side, okay. If we draw a semicircle with AC as a diameter, again it will pass through D, because angle ADC is also 90 degree. Is that right? Now therefore what will happen, now we have got two circles, two intersecting circles, and they both are passing through D, and we have generated point E and F over here, E and F, and then if we draw a circle with BC as a diameter, which we know, if we draw a circle with BC as a diameter, we know that it will pass through E and F, provided these angles are 90 degree. So it will pass through E and it will pass through F. We already knew that. Therefore, three altitudes ADB, CF in this case happen to be the common chords of three circles, and these three circles are with ABBCCA as a diameter, and therefore they pass through DEF. All two circles at a time will pass through DEF, and then common chords will be ADBECF. So because common chords of three circles are concurrent, altitudes are concurrent. So this is yet another proof of concurrency of altitudes. Now in this lecture, another exercise is to find out different angles in the figure 3, which is given to be cyclic quadrilateral and which is simple. So using exterior angle of cyclic quadrilateral is equal to remote opposite interior angle, and inscribed angles are equal. These are the two equality of angles we have to use and find out different angles. Maybe let us do it. A, B, C, D, and there are exterior angles. So if ABCD is cyclic quadrilateral, of course we know that this angle is equal to this total angle outside will be equal to remote opposite angle this much. So there are many pairs like this. Inscribed angles are equal, therefore this angle will be equal to this angle. There will be 4 more pairs like this. Sorry, not this. This is opposite angle I have shown. Exterior angle. This angle will be equal to this. This angle will be equal to this. And vertex opposite is going to be this. So you have 1, 2, 3, 4 angles at one vertex which are equal to exterior and to interiors. Like this, if we keep working, we will get many angles equal in this diagram. I will request you find them out, decorate them with different notation so that you remember it forever. That is the activity only to cross check whether we have understood cyclic quadrilateral or not. Now, concurrency of altitudes, we have yet another proof where we have been given a triangle ABC and only 2 altitudes are drawn. This is 90 and this is 90. Okay. So if we join A into H, to be proved that this is going to be perpendicular to BC, the line AH to be perpendicular to BC. Now if you observe that this is 90, this is 90, therefore AFHE is a cyclic quadrilateral. If you make these angles x is equal to y, these 2 angles will be equal because of cyclic quadrilateral property of AFHE. Then you will also observe that yet another angle, this angle basically also should be equal to Z, because you have this cyclic quadrilateral and this angle is Z, this angle is Y, this angle Y is also equal to X. So if we consider cyclic quadrilateral AFHE, we have X is equal to Y, inscribed angles. If we consider cyclic quadrilateral BFEC, we have Y is equal to Z, again inscribed angles, and therefore these 3 angles X is equal to Z. However, angle B is common. Angle B is common too. So let us call this point D. So ABD, angle B is common, this is X. However, in triangle CFB, it is definitely 90 degree. So as CFB is 90 degree, angle ADB must be also 90 degree. Angle CFB equals 90 implies angle ADB equals 90, and hence if we join AH and extend, it will be perpendicular to BC. That is what is the proof of altitude concurrency. This is the third proof of altitude concurrency that we are discussing. First proof was parallelogram. Because perpendicular bisectors are concurrent, altitudes are concurrent. Second proof we discussed today, because 3 intersecting circles have common chords which are concurrent, altitudes are concurrent. And now this is by angle chasing. The third altitude that you will draw, because of cyclicity of quadrilaterals, third altitude you will draw is going to be perpendicular to BC. So these are the 3 different proofs of altitude concurrency that we have learned so far. Now, the last problem in this particular lecture is practice problem, where we have given few questions which we need to solve. Suppose triangle ABC, this is I and this is I1. So join I1, join I. Okay. This point where angle bisector X intersects the circumcircle, this point is called L. The first question to be answered is angle LBI equals angle LIB. LBI. Now, what is known in this particular configuration? This is internal angle bisector and this is external angle bisector. Therefore, they have 90 degree between them, that is known to us. This is also 90 degree between them, that is also known to us. Right? So now, basically, we are supposed to prove LBI. Now, out of LBI, this is B by 2. And if you observe, this angle which we wish to find out is A by 2. Let us call these angles A by 2 and A by 2. Okay, so this is A by 2 plus B by 2, that is LBI, A by 2 plus B by 2. And what will be this angle? LIB. So this is A by 2 and this side also it is B by 2 because it is angle bisector, and therefore exterior angle of triangle ABI is A by 2 plus B by 2. A by 2 plus B by 2. That answers our first question. LIC and LCI. LIC and LCI. Again they are same. This is C by 2 plus B. This is C by 2 and this is C by 2 plus A by 2. And this will be again A by 2. Okay, so similarly we have other result, second result also. This implies this is isosceles triangle, this is also isosceles triangle, therefore LB is equal to LI is equal to LC. L is equidistant from IB and C. L is circumcenter of IBC because it is equidistant. Now IB-I1C is cyclic quadrilateral, IB-I1C is a cyclic quadrilateral because opposite angles are 90 degree. At B we have 90, at C we have 90. L is the center of cyclic quadrilateral IB-I1C. Now, let us prove that LB is equal to LI is equal to LC. We have already proved. Now we have to prove is also equal to LI1. Now, this total angle is 90 degree and therefore the remaining angle here is going to be C by 2 and the remaining angle here is going to be B by 2. Why? Because A by 2 plus B by 2 plus C by 2 is 90 degree. Out of which A by 2 is available here, B by 2 is here, so remaining angle is C by 2. Here A by 2 is available, C by 2 is available, therefore remaining angle is B by 2. Now what should be this angle? That is the question. What should be this angle? How do we find that angle equal to? And how much is this angle? Claim is that angle is going to be equal to C by 2 here and B by 2 here. Well, okay, so how do we find it out? This is C by 2 and this is B by 2. Basically, this is 90 degree. This point is such that CLI is equal to LB. Okay, if we can find out this angle, this is going to be exterior angle of triangle BLI1. Now let us find out this angle. This total angle ABL is equal to B by 2 plus B by 2, that is B plus A by 2, and that angle here is again A by 2 plus A by 2. Okay, so angle addition of angle A and angle B is basically A plus B. Is that right? Yes. So measure of this angle must be equal to C. Oh, and AB subtends C angle here, AB subtends C angle here. Another reason why it should be C. And out of which this angle C by 2 is gone, therefore remaining angle is C by 2. So every time you need to think something different to get these answers, and these are not really mugged up answers. You just find out the properties. There are so many properties, you can do it in different ways, that this angle chasing, maybe every time we will do it in different ways. So this angle is C. Obvious reason is AB subtend C at C and AB should subtend L, C at L, and out of which C by 2 is used here, therefore C by 2 must be remaining. Similar case will be this side. Therefore you end up getting L as a midpoint of I1 and happens to be circumcenter of quadrilateral IB-I1C. Major angle BIC is 90 plus A by 2, because this is C plus A by 2 and this is, how much it is, B plus A by 2. So this is B plus A by 2, B by 2 plus A by 2. So A by 2 plus B by 2 plus A by 2 plus C by 2 is the total angle BIC, which happens to be equal to, because A plus B plus C by 2 is 90 degree, these three added together is 90, therefore this is 90 plus A by 2. And because BICI1 is a cyclic quadrilateral, the supplement of this angle is going to be this angle, but it is B by 2 plus C by 2, which is 90 minus A by 2. So angle BI1C is 90 minus. So these are all small problems in lecture number 47. Hope you have enjoyed it. Maybe you can pause the video several times and try these problems independently, but we have to make it concise, and therefore I kept on answering all the questions. There are 5 camouflage problems given below. Try to solve them. See you in lecture number 48.